Hello, welcome you all. I'm Sudha Sekimuntu. I'm a researcher at Inner COE, and this webinar is conducted by PACK-NIN webinar series. PACK-NIN project. The aim of this project is to valorize lignocellulosic biomass for value-added application. And part of this webinar, today our speaker is Dr. Tugrul Yumak, and he's going to make a presentation on lignocellulosic biomass-based activated carbons for supercapacitor applications. And before he starts, I would like to introduce about him. And Dr. Tugrul Yumak is an assistant professor at Sinop University, Turkey, and he received his B.Sc in chemistry from Ankara University in 2008 and completed his Ph.D. in physical chemistry in 2016 in the field of thermochemical conversion of biomass into valuable chemicals and biochars. Then he worked as a postdoc scientist in the Department of Mechanical and Aerospace Engineering at West Virginia University from 2017 to 2018. And during this time, he focused on the synthesis of highly ordered mesoporous carbon from waste biomass and its electrochemical characteristics. And he's currently managing the materials and the energy storage research group in the Department of Chemistry at Sinop University and focusing on the synthesis of mesoporous carbon materials, carbon-based composites, and energy storage applications. So with this introduction, I'm happy to give this floor to Dr. Yumak, and please go ahead. Thank you.
Okay. Thank you, Dr. Suta, for the kind introduction, and hello, everyone. I would like to thank you all for giving us your precious time, especially on these hot summer days. And again, Dr. Suta, for inviting me to make this presentation. My speech is about the lignocellulosic biomass-based activated carbons for supercapacitor applications, as you see. My speech will be in 4 parts. I would like to start with energy storage and supercapacitors and the properties of an ideal electrode material for EDLCs. Later on, I will continue with the activated carbon formation from lignocellulosic biomass via the activation techniques. And since the high temperature is mandatory for formation and high surface area in the I will mainly focus on the thermal behavior of lignocellulosic biomass and the disadvantages of the activation process. And of course, what can we do to overcome this issue? Finally, I am planning to talk about the confusing part of which techniques gives what information or which information and what should be considered for talking about the capacity and electric area. Simply put, energy storage is the ability to capture energy at one time for use at a later time. Storage devices can save energy in many forms like chemical, kinetic, electromagnetic, and thermal, and convert them back to useful forms of energy like electricity. A common way of categorizing storage technologies is by their power ratings and discharge times. Lower power ratings and shorter discharge times are labeled as suitable for helping with power. Shows how a variety of storage options have been compared. Please note that the batteries and supercapacitors can vary significantly in terms of their power ratings. Ragone plot gives more detail about power and energy density of an electrode material or energy storage device. As you see, the Ragone plot is generalized and sharply separated. However, in today's conditions, some of the batteries and supercapacitors represent the same energy and power density. Being at the same point made them supercapacitors and batteries are rival runners in the hybrid vehicle research and development. But I believe they are the two sides of a coin. The terms energy density and power density can be usually confusing. The analogy between a cardboard and a bucket is quite helpful to understand the difference and the bond between the batteries and supercapacitors. A supercapacitor, also called an ultracapacitor, has a capacitance volume much higher than the other conventional capacitors, but with lower voltage limits. That bridge the gap between the electrolytic capacitors and rechargeable batteries. Supercapacitors have a far higher specific power, meaning they can provide a higher current compared to a battery. So supercapacitors are used in such applications that require high instant power needed, like hybrid vehicles, alarm systems, or starting off the high power generators. Based on the energy storage mechanism, supercapacitors can be classified into two groups. The first one is EDLCs, and the second one is pseudocapacitors. In EDLCs, no electrochemical reaction takes place on the electrode, and the energy is stored by pure physical accumulation at the electrode-electrolyte interface. In the case of pseudocapacitive materials, the energy is stored directly by fast and reversible redox reactions. The thickness of the double layer is much smaller than that of the conventional separators. They have very high capacitive performance and higher power densities. In EDLCs, carbon-based materials are used as electrodes or electrode active materials, while metal oxides, metal hydroxides, and conducting polymers are used in pseudocapacitors. Here you can see the requirements for a good carbon-based electrode material. It should have an accessible large surface area, the proper distribution, of course, good surface wettability, high electrical conductivity. We should control the microstructural morphology, and we need long cycle and thermodynamic stability. Energy storage applications. However, the problem is that they are so expensive. But we conduct some lab-scale experiments with decorated carbon-based materials to verify the effect of decoration. Among the carbon-based materials, biomass-based activated carbons with 3D networking structure, abundant mesopores, and high macroporosity are good candidates for the electrode active material. 3D networking structure provides low electronic resistance, while the abundant mesopores provide low ionic resistance and a high transport rate of electrolyte ions. Pore size less than 1 nanometer limits the electrolyte mobility, so we require the ideal pore size range of almost 1 to 10 nanometer for an ideal activated carbon electrode. The biomass-based activated carbons are more abundant, cost-effective, and environmentally friendly materials compared to coal and petroleum-based ones. As well known, biomass is simply an organic matter, the source of which can vary significantly. Animal remains and byproducts, plants, forest products, residues, and even residues left over from the agricultural industry can all serve as a source of biomass. Biomass can be converted into a high value-added product, activated carbon by activation techniques. Put it simply, the activation process is mixing the biochar or as itself the activation agent and increase the temperature. The objective of the process is to enhance the pore volume and increase the porosity. The activation process can be performed by two different methods. The first one is physical activation. We use generally steam or carbon dioxide, while some alkalines, acids, chlorides can be used for chemical activation. The mechanism and the operating temperature of activation depends on the type of activation used. For example, in the case of zinc chloride, the porosity is created by the spaces left by the reactant after washing, while KOH, the reagent starts the activation process at higher temperature, above 700 C. In addition, the nature of the biomass and reactions that occur during the activation process led to the formation of heteroatom containing surface functional groups. These groups are very effective in determining the hydrophilic character, so the wettability and the charge of the activated carbon surface. I don't want to bother you, but I would like to briefly talk about the activation mechanism, both from the particle structure point of view and chemical reactions during activation. According to the Franklin structural model, activated carbon is a non-graphitable carbon material that contains oriented graphite parts, graphitic regions, and regions that cannot be graphitized. The physical activation process occurs non-selectively on the carbon surface and gradually reduces the basic domain size, while the chemical activation process occurs primarily in non-graphitic parts within the material. However, water and carbon dioxide molecules are generated during the chemical activation. And so the chemical activation can also reduce the basic domain size because physical activation occurs at the same time. Furthermore, since the chemical activation reduces the amount of non-graphitic parts, chemically activating a carbon material at a relatively high temperature can enhance its crystal structure. In other words, chemically activated carbon materials contain relatively low proportions of non-graphitic parts. It is very important to note the reactions in terms of chemical kinetics. As I said in the previous slide, the physical activation consists of thermal decomposition of the carbon source material, followed by the introduction of the activation agent. The process is slow oxidation in which the oxygen reacts with the carbon atoms, generating carbon dioxide. This slow oxidation mechanism generates porosity. The oxygen added into the system is also partially chemsorped on the surface, generating oxygen-containing surface functional groups. Carbon dioxide and steam generate different pore size distributions due to the site-produced inhibitors. The inhibitors are carbon monoxide in carbon dioxide activation and hydrogen in steam activation. And this enhances the microporosity during carbon dioxide activation and mesoporosity during steam activation, with the consequent formation of the different functional groups, but they both oxygen-containing functional groups. In carbon dioxide activation, carbon and oxygen complexes are in the first phase created, and they are so stable. And some of the complexes can decompose into carbon monoxide, leaving a free carbon surface for an additional reaction. In the KOH activation, KOH, potassium hydroxide, dehydrates to transform into potassium oxide at almost 400 C. Then the carbon is consumed by the reaction of carbon and water with the emission of hydrogen. The potassium carbonate is formed by the reaction of potassium oxide and carbon dioxide, which is produced in the equation 3 in the right side. Then the activation starts with reaction in equation 5, and it further proceeds via the reaction of metallic potassium and potassium with KOH to potassium oxide. At about 600 C, the KOH is completely consumed. So the S-formed potassium carbonate significantly decomposes into carbon dioxide and potassium oxide at temperatures higher than 700 C and completely disappears at 800 C. Moreover, the resulting carbon dioxide can be further reduced by carbon to form carbon monoxide at higher temperatures. The potassium compounds, potassium oxide and carbonate, also can be reduced by carbon to produce metallic potassium at temperatures over 700. So, two different reaction pathways, both resulted in an increase in the surface area and the development of the porous structure. However, each process leads to physical activation, makes it possible to obtain narrower pore size distributions compared to chemical activation. And chemical activation leads to higher packing density. And this brings out a positive effect on the volumetric absorption capacity. Researchers from Finland reported the effect of some process parameters on the main properties of activated carbon produced from peat by steam activation. As in the slide, the coefficient plot illustrates how a factor affected the selected response. The higher columns indicate a higher impact, and the impact can be either positive or negative. For physical activation of peat, as you see, the holding time and steam speed are the most influential parameters on pore size distribution responses. However, the rotation speed also seemed to have an impact on porosity formation, which was likely due to the better contact between the biomass or biochar and the activating agent. Thus, the reporting process, an increase in the rotation speed of the reactor instead of steam feed, the amount of the chemical activation agent or the ratio of activation agent to biomass or biochar should be considered for the chemical activation process. Apart from this, please note that the type of the biomass is the most determinative factor in activated carbon properties. Lots of work can be found focused on the activated carbon production and their electrochemical energy storage characteristics. In the slide, as you can see some examples, we have different types of biomass ranging from trees to human hair, from full felt to anthracite. I took only the chemical activation agents, mostly KOH. As you see, the activated carbon obtained by KOH activation from pine leaves has an extreme surface area almost 4,000 square meter per gram, and the specific capacitance is almost 140 farad per gram. While the wool felt-based activated carbons has almost 1,100 square meter per gram, and they have nearly 160 farad per gram specific capacitance. Unfortunately, it is impossible to put all the experimental details here, and we cannot find them in the papers. But it is clear that there is no direct correlation between the surface area and the specific capacitance. In addition, not only the surface area, but also the surface morphology, chemistry, and the shape of the pores are effective on the capacitive performance. Therefore, the effect of activated carbon formation parameters on the determination and evaluation of the capacitive performance is quite complicated. Up to now, I talked about good. Now it's time for the challenges during the controlling or tailoring the surface characteristics of active carbons for enhanced energy storage capacity. The first issue is controlling the pore size distribution. Again, we expect a proper distribution of micro and mesopores for better ion transport and charge storage. But we don't know the exact number, volume, or ratio of pores that we need. So now we are playing with the experimental parameters to find out the best one. The template approach is a promising solution. However, there are some drawbacks such as high cost, removal of template, and not being so feasible for large scale. Besides, the templates have uniform sized pores. For example, the activated carbons synthesized by zeolite templates consist of curved and single layer graphene frameworks, thereby affording uniform micropore size. It's almost 1.2 nanometer. Developed microporosity and very high surface area, almost 4,000 square meter per gram. Unlike the well-known ordered mesoporous carbons obtained by using mesoporous silica templates. Perfect results we have, but again, we need lots of mesopores to ensure the mobility of electrolyte ions to the micropores. So, it is clear that we need much more effort to synthesize new templates with micropores and mesopores together in the same structure. The origin of the other problem is the thermal behavior of biomass components. As you know, cellulose, hemicellulose, and lignin are the main components of biomass. Cellulose is a linear polymer composed of many glucose units, and it is mostly crystalline. And hemicellulose is almost 200 to 400 units branched or linear polymers comprised of 5 or 6 carbon sugars. And the final component, lignin, is a networked polymer composed of phenyl propane units. During the heat treatment on carbonization or activation, the amorphous part, most of lignin, began to wax at glass transition temperature. And this viscose structure inhibits the heat transfer and indirectly leads to the negative effects on pore formation. Lignin has a lignin's glassy transition temperature, Tg, is far below the temperatures required for carbonization. Therefore, it must be pretreated to prevent softening, to overcome this. Air stabilization, which is a simple and cost-effective method of thermostabilization, may be an option. Reactions occurring during the thermostabilization increase the Tg. As the temperature increases at very slow heating rate, then the Tg can increase faster than the temperature, maintaining the material in the glassy state, non-tech. And at higher heating rates, the thermostabilization reactions are not able to maintain the Tg greater than that vitrifies, entering the techy liquid rubber state, fusing together. Before the carbonization or activation process, pretreatment with air can help to enhance the porosity. However, the air stabilization process takes 2 minutes lower than 0.1 C per minute. So the problems keep increasing somehow. In this section, I would like to briefly talk about the necessary information and analysis techniques when evaluating the capacity performance of the electrode material or a supercapacitor device. The value of specific capacitance can be calculated by cyclic voltammetry, LCV, or electrochemical impedance spectroscopy, and galvanostatic charge-discharge curves. Among them, the GCD is the most reliable one. CV gives us information about the electrochemical chains of an analyte or of a material that is observed on the electrode. In EDRCs, a quasi-rectangular shape indicating an excellent capacitive behavior is expected. In GCD technique, the specific capacitance is calculated from the discharge curves after excluding the IR drop. However, the whole GCD curve gives the whole charge capacity and the most important one, the Coulombic efficiency of the electrode material. In EDRCs, the symmetric triangular shape of the GCD curves proves the capacitive behavior is expected, and thus it is not easy to simply compare the reported capacitance values, which are measured using different techniques. Also, the parameters during the analysis are very effective. The other one is electrochemical impedance spectroscopy is widely used to determine the resistance of a supercapacitor or electrode material consisting of electronic and ionic contributions. The Nyquist plots obtained, or the BOT plots obtained from the electrochemical impedance spectroscopy data, is used to determine the combined resistance of intrinsic resistance of electrode material, ionic resistance of electrolyte, and contact resistance between the electrode and the current collector, and the electrode conductivity, and also charge transfer resistance. And the other parameter is the self-discharge behavior. The self-discharge can be defined as the charge holding ability. It can be determined by monitoring the voltage versus time during an adequate rest time after a full charge. And this charge and rest test should be applied to volumes obtained. Since there are lots of parameters in the origin of electrochemical analysis, it is too hard to make a meaningful comparison. So energy and power density help you to put your electrode material or device in some place in a Ragone plot, and you can easily compare it with. And capacitive performance, more precisely, the calculation of the capacitive performance is highly dependent on the type of the electrochemical cell and the experimental parameters of the method. In the slide, 4 different types of electrochemical cells you see. In most cases, the 3-electrode cell is used, and it is the most useful and the cheapest one. However, closed systems like switch lock and coin cell or punch cell are preferred because the results are more realistic. A full electrode is a mixture of electrode active material, a binder, and a conductor. The specific capacitance decreases with the increasing amount of binder because the binder places on the pores. But the binder put the electrode material the minimum amount of binder for a perfect electrode. Besides, the thickness of the electrode is also a determinative parameter of the capacitance, and commercial cell electrode thicknesses range from about 10 nanometer thick for high power density to several hundred microns thick for higher energy density. And also the electrolyte is very important, and common aqueous electrolytes include 6 molars of potassium hydroxide and 1 molar of sulfuric acid. Since energy stored is related to the square of the voltage, organic electrolytes are currently used in commercial capacitors due to the wider electrochemical working voltage window. It's about 2.7 volts as compared to about 1 volt for aqueous electrolytes. And ionic liquid electrolytes are also being adopted due to their increased electrochemical windows and improved thermal stability. In conclusion, the utilization of naturally abundant biomass to prepare biomass-derived carbons with high functional performance in supercapacitor application is green, cost-saving, and sustainable. Even though the state-of-the-art research on the biomass-derived carbon for supercapacitors have shown relatively higher specific capacitances compared to conventional carbon materials, and excellent high rate performance and cyclability, several critical challenges are still associated with the development of biomass-based carbon for supercapacitors. The first one is the carbon yields of the biomass differed according to the chemical and elemental compositions of the precursor, which were in the range of 5 and 50% by weight. Some of the biomass-derived based activated carbons with excellent capacitive performance are obtained from low carbon yield precursors, which in turn sustainably limit their large-scale production. Maybe the major carbon contributors such as lignin, ketene, or creatine can be extracted from the precursors and then purified and concentrated prior to decarbonization to achieve a high carbon yield. And the second one is the energy density. Even though the specific capacitance of the biomass-derived or biomass-based activated carbons can reach relatively high values, above 400 farads per gram. They are still not comparable to the pseudocapacitive materials, which can reach specific capacitance above 1000 farad per gram. And maybe heteroatom doping such as nitrogen, sulfur, boron, or oxygen, or nanocomposite of composites of biomass-based carbons And maybe coating with the conducting polymers and metal oxides may help to increase the energy density. And the last one, maybe the most important one, is the microstructural control. Until now, the synthesis and the formation of biomass-based activated carbons almost always followed by unattended process. As a consequence of this ignorance, the formation of random arrangement of the graphitized structures and distribution of the macro, meso, and macropore lowers the charge transport efficiency and ion transport efficiency. Therefore, it is obvious that we need more engineering for the synthesis of hierarchical porous carbon. And finally, I would like to thank all the audience here again, and of course, my team and the Scientific and Technological Research Council of Turkey, TÜBİTAK, for the financial support for my projects.
Okay, thank you very much, Dr. Tugrul, and for the nice presentation.
You're welcome.
Yeah, and I apologize for the disturbance during the talk because Dr. Tugrul is already on vacation, but he managed to connect with us. So thank you for that. And we have received plenty of questions. So I start with first from Saijal. I'm sorry if I don't know I pronounced your name correctly. And the questions are whether meso or micro porosity should be maximum for maximum capacitance. How to introduce 3D interconnected pores. So
I could.
Okay. I think you lost the connection. Okay. Again, I repeat, whether meso or micro porosity should be maximum for maximum capacitance.
And also question right in the comments.
We need more macropores and mesopores. The macropores are responsible for the charge storage, and the mesopores are responsible for ion transport from electrolyte to micropores. So we need a proper distribution of mesopores and micropores. We need both of them.
And how to introduce 3D interconnected pores?
Sorry again?
How to introduce 3D interconnected pores? 3D interconnected pores.
Yeah. The question is about the formation of this 3D network?
Yes.
Yeah, the 3D network is, as you see in the slide, the biomass itself is a 3D network. And in the activation process at higher temperature, we always said that this network collapse and for the pores formed again. But in fact, it is not true. The lignin not collapse totally and not decomposes totally. So the lignin, the situation of the lignin is the origin of this 3D network. Lignin is responsible for this 3D network.
Okay, then next question from slide number 15.
Okay, here's 15.
Yeah, what is the third plot other than CV and GCD?
This one at the top of the slide is GC plot and GC curves. And this plot, now I think you see at the bottom of the slide is GCD curves. And this one is the self-discharge curves.
Okay, thank you.
We talk about the quasi-rectangular shape of the GC curves, indicates the capacitive behavior, and the triangular shape in GCD curves indicates the perfect capacitive behavior.
Okay, thank you. And next question from Veerapandian. Lignocellulosic biomass is highly heterogeneous and composition differs with respect to plants and location. Does this heterogeneity affect the capacitance?
Yes, it affects the capacity and it decreases the capacity. At the result, at the final product, we need micropores and mesopores, and this nature of the biomass affects all this pore structure. But as you know, other than cellulose and micellulose and lignin, the biomass has other components like ashes, some minerals, and they also affect negatively the capacity performance.
Okay, thank you. And the next question, what are the challenges to achieving high performance activated carbon from biomass for supercapacitors to the market?
Oh, actually, our basic problem is we don't have hierarchical porous structure for now for biomass-based activated carbons. We usually have more macroporous structure or mesoporous structure, but we need both them together in the same structure. So we need not orders or highly mesoporous carbon. We don't need this. We need hierarchical porous carbon. We have lots of macropores and mesopores and also macropores, micropores and macropores to put these capacitors into the market. So we need lots of engineering. It is not so easy.
Thank you. And again from Sajal, how can optimize the amount of binder and what things to be considered?
Oh, you can optimize the binder with changing the binder amount in the electrode slurry. In most cases, we use 8% electrode active material, 10% binder, and 10% the conductive material. In my works, I use carbon black as conductive material and PVDF for binder. And you can decrease the binder and increase the binder in several experiments and look at the results so you can find the optimum binder. The optimum binder amount is dependent on the electrode active material. So you should do some experiments.
Thank you. By doping the biomass with heteroatom can improve the capacitance?
Yes, we talk about this. Okay. You can use some heteroatom. For example, nitrogen is currently used, and boron maybe you can use. We have oxygen containing surface functional groups, phenolic groups, alcoholic groups, carbonyl and carboxyl groups, and they enhance the wettability of electrode surface, so increase the specific capacitance indirectly.
Okay, again, next question is how can we recognize and distinguish the EDLC and pseudo capacitance?
How can we
recognize that and recognize and distinguish the EDLC and the pseudo capacitance through any electrochemical methods?
We should do some cyclic voltammetry experiments in the pseudo-capacitive material. As you see, this belongs to EDLCs, but in pseudo-capacitive materials, you will see some peaks according to the originated from the redox reactions on pseudo-capacitive materials. The CV is quite different for pseudo-capacitors and EDLCs.
Okay, then finally, how the purity of crystalline phase of active material affect the capacitance?
Oh, actually, I don't know this because the biomass, as you know, is not a pure material. It is very heterogeneous. We make some experiments to, I guess the homogeneity, when you increase the homogeneity, the specific capacitance will increase. But when you use the homogeneity of the electrode, the specific capacitance increases, but the other parameters, for example, self-discharge and resistance, can decrease. So if your purpose is to increase the specific capacitance, you can increase with the homogeneous electrode. But if we are talking the total capacity performance, the resistance can increase, and we don't want this.
Okay. And finally, again, he asked, he managed to ask the same question again. How can we determine the contribution from EDLC and pseudo capacitance, and how much percentage is due to pseudo capacitance?
Oh, it's a good question. So we should use CV analysis again, but you should use very lowest scan rates. For example, 0.1 millivolt per second. When you use lower scan rates, you can see the capacitive effects of the surface functional groups or the adons. Maybe you can decorate the activated carbon with metal oxides. And if you use CV analyzers with very lower scan rates, you can see the effect of this metal oxide, the reduction and oxidation peak of metal oxide in CV. And you can see only this one. If you increase the scan rate, it is impossible to see the effect of this pseudo capacitance.
Okay, thank you. And one final question from my side. Can we do any kind of lignin modification? Because you mentioned that the TG gives some trouble when you make the carbonization. So can we make some kind of... sorry.
What kind of decoration are you talking about?
Kind of modification to change the TG?
Yes, I only know the air stabilization, but if something, the TG is about the amorphous structure. If you change the amorphous structure of lignin, why not? We can change the TG. It can be a good project subject.
Okay. And can we use also some kind of nanoparticles or transition metal-based oxides like titanium oxide?
Yeah, the metallic nanoparticles or metal oxide nanoparticles are generally used to decorate some carbon-based materials.
Okay. So I think it's... thank you very much for answering all our questions and clearing the doubts. And it's really a wonderful presentation. And thank you very much for this talk. And thank you all the audience. I thank you all the audience. So if you want to see this webinar online, please follow the InnoRenew YouTube channel. There you can find this video for a long period of time. But it will upload it in maybe in 1 week to maximum within 2 or 3 weeks. And thank you. And the continuation of this webinar will be on September on the topic of Lignocellulosic biomass-based materials for packaging application. So if somebody interested on this topic, please join the webinar in coming series. Thank you very much. Yeah. Thank you very much. Thank you all.